today's video lecture, we are going to step into an important section of linear algebra, which is a subspace of a vector space. So, in last lecture, we had seen what is a vector space and what are some examples of vector spaces, and you verified them all during the assignment section. Let's see how we can define a subspace first of all. So a subspace, for defining a subspace, basically we need a vector space V over the field F. A subspace of V, of this vector space, is actually a subset W of V, which is itself entered a vector space over the same field F, with the operations of the vector addition and scalar multiplication that is happening inside V. That means if we have a vector space V over F, which has the operations vector addition and scalar multiplication, W over F is nothing but a subset inside this V, which is itself a vector space. So to summarize that definition, this W is a subset, it is non-empty. So the non-empty part is very important. W is a non-empty subset and it satisfies the four properties of vector addition that is happening inside V. Also W satisfies all the four properties of scalar multiplication that is happening inside V, and that will imply W to be a subspace of V. So inside W we know that if we have two elements alpha and beta in W, the vector alpha plus beta is again in W, because W is a subspace, it is a vector space. The zero vector will be in W, and for each alpha in W, the vector minus alpha is in W. For each alpha in W and its scalar C alpha will be in W, or the commutative and associative property of vector addition is satisfied, and all the other four properties of scalar multiplication. So the properties of scalar multiplication need not be checked actually, because all the elements inside W are also in V. So already the properties of commutativity and associativity holds there. So that will also hold in W. So why we don't need to check the properties of scalar multiplication? Because the property of the operation is the property that is happening inside V itself. So no need to bother to check for that. So that's how we summarize it. Like if you are given a subset, non-empty subset of V, you have to check whether it is a subspace. In the normal sense, what will you have to do? You'll have to check whether, yes, it's given non-empty, and then you have to check the four properties of the vector addition and in turn four properties of scalar multiplication. So we were just saying that if we find the first three properties of our vector addition, that is enough for us. So the rest of them will hold. Okay. So even checking all the three properties is also a lot of work. So how to easily verify W subset of V is a subspace of the vector space V. So that makes us go to the theorem 1, which says a non-empty subset W of V is a subspace of V if and only if for each pair of vectors alpha comma beta in W and each scalar C in F, the vector C alpha plus beta is again in W. That is, we just have to check whether C alpha plus C alpha plus beta belongs to W whenever alpha and beta are in W. Okay, so let's call it the C alpha plus beta property of a subspace. Okay, so how to prove this? So we are assuming that W is a non-empty subset of V such that C alpha plus beta belongs to W for all vectors alpha comma beta in W. That means we are assuming the right hand part of the if and only if clause. That is, for each pair of vectors alpha beta in W and each scalar C in F, the vector C alpha plus beta is again in W and all scalars C in F. Okay, since W is non-empty, there will obviously exist a vector rho in W. Fine. And what did we assume? That we assume that this W has the C alpha plus beta property, right? For every alpha comma beta belongs to W and C belongs to F. So take C is equal to minus 1. Where does the C come from? It is coming from F. It is a field. F being a field, it has the multiplicative identity 1. And of course, then it will have the additive inverse of 1, which is minus 1 inside the F. So C is equal to minus 1 will belong to F. That's certain. And take alpha and beta both to be rho. Okay. We know that rho is in W and we are taking alpha and beta is equal to rho and C is equal to minus 1. Substitute it in C alpha plus beta. That is minus 1 into rho plus rho. Okay. That is equal to 0. Why? What is this plus sign standing for? It is the plus sign of the vector addition inside the vector space V. So inside the vector space V, we know that minus rho plus rho will be 0 because we defined that, and that is in the norms of our verification of a vector space. So minus 1 into rho plus rho, which is equal to 0, belongs to W. That means the additive identity of W0 is existing inside. Okay. Then if alpha is any vector in W and C be any scalar, then in that case, what are we doing is we are taking C is equal to minus 1. Let alpha is equal to alpha, beta is equal to 0. Beta is equal to 0. We understood that it belongs to F now, right? Sorry, it belongs to W. We proved it now. So we are taking the C alpha plus beta property. That means minus 1 into, instead of alpha, we have alpha itself. We have assumed that alpha is in W. Plus, instead of beta, we are taking 0. So that means minus alpha is in W. That means for any alpha, there exists the inverse of additive inverse of alpha, that is in W. Okay. Finally, if alpha and beta are in W, if alpha and beta are in W, take C is equal to 1, alpha is equal to alpha, beta is equal to beta. That means alpha plus beta. What that can be written as 1 into alpha plus beta, that belongs to W. So what did we prove? We proved the first three properties of vector addition. That means if you have two elements inside W, there the addition of those two vectors will be inside W. If you have an element, you have the inverse in the inside W, and the element plus its inverse, the vector sum of element and its inverse is equal to 0. Okay. So that means rest of them, as we said earlier, we need not check about associativity. It will be obviously associative because associative and commutative, because that is happening inside V itself. V is already a vector space. And also the scalar multiplication will hold in turn. So thus W is a subspace of V. So we got that from the right hand side to left hand side we proved. So what we proved is RHS implies LHS is proved here. Now we have to prove LHS implies RHS. So if W is a vector space of V, we are taking it. And then alpha, beta are in W. Suppose we take it and C is a scalar coming from F. Then we know that C alpha will be in W. Alpha belongs to W and C belongs to F means C multiplied by alpha is inside W because that is the property of scalar multiplication. So that is true. And if C alpha belongs to W and beta belongs to W, C alpha plus beta belongs to W by the property of vector addition. So we proved LHS implies RHS too. That means the if and only if condition is proved and verified. So this is an important theorem where we check for a non-empty subset of a vector space if it becomes a subspace of it or not. So let's call it the C alpha plus beta property of a subspace. Fine. Now we will see some examples and we'll verify whether each of them is a subspace of a vector space or not. If V is any vector space, definitely V is a subspace of V. V is a subset of V and V satisfies all the properties with respect to the vector addition and scalar multiplication over F. So V is a subspace of F. And also the subset consisting of the zero vector only is also subspace of V. So here what we said is the W is equal to set 0 subset of V over F is also 0 is also subspace and it's called the zero subspace of V. So V is a subspace of V itself and also the zero subspace is subspace of V, the trivial subspace. Now consider F raised to n. F raised to n is nothing but F raised to n is nothing but F cross etc cross F n times. Okay, that means it will have the elements to be n tuples. Okay, so the n tuples will be the ordered like this: x1 embraces x1 comma x2 comma etc comma xn. Okay, so that is our vector space set of all n tuples. We just think about Rn. So the set of all n tuples inside Rn. Okay, under the normal component-wise addition and scalar multiplication, the field will be F here. Okay, that means here the vector space is V is equal to Fn over the same field F. If you are thinking about Rn, that means Rn over R. R is definitely a field, as you know. Now we are going to make the subspace. For making the subspace, what do you do? Uh, see this W1. W1 is the subspace we are talking about. We are going to make the first one 0. Okay, first entry 0. The rest of them x2, etc., xn. Okay, all of the entries coming from F. So that is a subspace. You can check for the three properties. The first property is uh, definitely the additive identity, which is the n tuple which has all entries to be 0. That will be the additive identity, every element, every n tuple inside W1 will have its inverse. Just make the negation of the entries and add, you get 0, right? And also if two elements are coming from W1, when we add, the element will be in turn in W1. And rest of the properties are obvious: associativity, commutativity, effect, radiation, and all the properties of scalar multiplication. You need not verify, they are satisfied. So this W1 is a vector space of this Fn over F. Okay. And do you have an example for a subset of Fn which is not a subspace? You can check for it. That is W2. W2 is written as set of all elements of n tuples such that the first element is 1 plus x2, comma x2, comma x3, comma etc. xn. It is definitely a subset of this Fn over F, uh, but it is not. But is but it is not a subspace. Why is it not a subspace? Because you can think about it a moment. Yes, it is not a subspace because the n tuple having the zero entries, which is the additive identity which would have been in W2, will not be in W2 because the n tuple 0, 0, 0, etc. 0 is not of the form which is written here inside this W2. So that is an example for a subset of V which is not a which doesn't work out as a subspace of this vector space. The third example is a set of all polynomial functions over F, uh, which is a subspace of the set of all functions from F. Okay, we are taking all functions from F into F, and the field will be F itself here, the same field. The subspace we are talking about is W is equal to the polynomial form kind of functions, f of x is equal to this. And the entries, definitely the constants are coming from F. So if you know that if you add two polynomials, that polynomial will be again you get a polynomial. The zero polynomial will be the constant function 0, and the negation of the constants coming, coefficients coming, can make a polynomial and its additive inverse. So definitely that is a vector space. Then the fourth example is we are taking the vector space to be the set of all n by n matrices over a field F. Okay, that means the entries are coming from F, and all the scalars are coming from F. Okay, then the subspace we are given is the set of all symmetric matrices uh, from among the n by n matrices. So you know that symmetric matrices are of the form like this, right? The You have the diagonal entries coming here, and if an entry is A12 in the first row, second column, the entry in the first column, second row will be the same mirror image. So think of this as a mirror. If this is a mirror, whatever elements are sitting here, that reflects over. This will be, these both are the same, these both are the same, these both are the same, and so on. So that is how a symmetric matrix looks like. So we are saying that these matrices, uh, the set of all such matrices form a subspace of the set of all n by n matrices over F. Okay, so you can verify it rigorously. It is very simple. You have to verify all the three properties. If you have two symmetric matrices, add them. Definitely, they will. You will get a symmetric matrix. Then the zero matrix will be a symmetric matrix. And if you have a symmetric matrix, then take the negation of the entries and add them, you get 0. That means you have the inverse too. The inverse of a symmetric matrix is also a symmetric matrix. So both all those three properties being checked out, we can end up saying that the set of all symmetric matrices form a subspace of the vector space of all n by n matrices over F. Now, the fifth one we are going to mention is first of all, we'll just define what a Hermitian matrix or self-adjoint matrix. Such matrices are matrices with entries coming from the set of all complex numbers. Okay, and the Hermitian matrices are those matrices such that they will the entries just if A is a matrix, then the A is equal to A transpose the whole conjugate. So you have to take the conjugate of you have to take the transpose of the matrix and then conjugate it. Okay, and if A is equal to that, so these are the same. These are the same. They are equal. Okay. So if that happens, we call A as a self-adjoint matrix or Hermitian matrix. So in smaller classes, while we were dealing with Hermitian matrices, you might have noted that the diagonal elements entries of the of a Hermitian matrix is equal to Z and W because we are transposing and we are equating it with the conjugate. So then the imaginary part should be 0. So you have the diagonal entries to be real, and every other element, if this is a if you're thinking about a 2 by 2 matrix, what happens is the diagonal entries will be real numbers, and the other off diagonal elements will be, if this is x plus iy, then the corresponding mirror image, it will be not a mirror image, it will be a conjugate mirror image. It's called conjugate mirror image. That will be x minus iy. Okay, so the information there is set of all such Hermitian matrices is not, please understand that it is not a subspace of the space of all n by n matrices over C. It is W is equal to the set of all Hermitian matrices is not a. Why is it not a subspace? Suppose if A is Hermitian, okay, we know that the diagonal entries will be real numbers. Okay. Now we are taking, since we are dealing with matrices over C and the field is F. Okay. Here the field is F. The field F is the set of all complex numbers. So I is a complex number. So I into A is a matrix. So I into A, think about this as a think about I being multiplied with this 2 by 2 matrix. Then what do you get? You get IZ I into X plus I by I into X minus IY, and this is IW, right? But the diagonal entries now have changed to uh, a complex number. It is not a real number. That means it is not a symmetric, not symmetric, it is not a Hermitian matrix. So that means the property about scalar multiplication will be not um, satisfied here. So if we take the field to be C, we are saying that the subset will not form a vector space. Now, if we are taking the field to be R, then it's okay because we don't have complex number to multiply with matrices. So that will turn to be set of all n by n. complex Hermitian matrices to be a vector space over the field are of real numbers, but they are not a subspace of the space of all n by matrices over C. So that means the fields also matter to us while checking about subspaces. Okay. The next example is we are thinking about the solution space of system of homogeneous linear equations. A system of linear equations can be written in the matrix form like this. If A is a matrix of m by n order x n cross 1, this will be the solution of this matrix of this equation is equal to 0. This n by 1 matrix will be the solution vector of this homogeneous equation. Homogeneous means the right hand side will be equated to 0. The coefficient b will be 0. Generally, we write system to be Ax is equal to b. So here the b will be 0. Okay, so what is our set? Set is set of all x which is having the order n cross 1 such that they are the solution set of Ax is equal to 0 is a subset of V which is equal to set of all n by 1 vectors. Definitely it's a subset, and also it is non-empty because 0, the n by 1 vector which has all 0 entries will be inside W, so it's non-zero, right? So, what should we verify here? I'll just give you a hint. That means if x comma y are coming inside W, we have to prove that by the Cx plus C alpha plus beta property. Earlier we said proved in the theorem. We have to prove that Cx plus y belongs to W. So for an element to belong to W, what should that element be? That element should be a solution of Ax is equal to b. So Ax is equal to 0. That means we have to prove A into Cx plus y is equal to 0. We know that x comma y belongs to W will imply to us Ax is equal to 0 and Ay is equal to 0. Right? So if A into Cx plus y is equal to 0, yes, in order to open this out and say C into AX plus AY is equal to 0, you have to think about this lemma, which is a very logical lemma you can prove by yourself. If A is an m by matrix over F, B and C are n by P matrices over F, then A into DB plus C is equal to DAB plus AC. That means it is showing connecting the distributivity property between matrix addition, matrix multiplication, scalar multiplication, everything is coming in between. Prove it. It is a very easy verification. So by this lemma, we can say that A into Cx plus y is equal to, by the lemma, you have to prove this. So to prove this by lemma, we can say that, so you have to prove. By lemma, you can say that this is equal to C into Ax plus Ay. But we know Ax is equal to 0, Ay is equal to 0. That means this will be 0 proved. So that's how the example 7 goes with the help of the lemma sitting here. You have to just work out this lemma, which is very logical. Just multiplying and adding the entries of the matrices along with the scalar multiplication. Also, if dB plus C into A, that is equal to D into dA plus CA, the same logic applies here. Then we goes to the next information, which is if V is a vector space over the field F, the intersection of any collection of subspaces of V is a subspace of V. So let Let's assume we are taking a collection of subspace of V and we are calling it set Wn or set Wa, or suffix a. Okay, and let W is equal to intersection over A, WA be the intersection. Okay. So how did we define capital W? W is the set of all elements which belong to every element, every set WA. Okay. So you have to prove that this W is a subspace of W of V. Since each WA is a subspace, each must contain a zero vector, right? So 0 vector will be inside the intersection 2, that is 0 belongs to W, it is non-empty. Now if alpha and beta are vectors in W and C be a scalar, by the definition of W, alpha comma beta both belong to WA because they are inside W. Intersection means every WAs will have them. Okay. And because each WA is a subspace, definitely C alpha plus beta will be inside every WA. That means C alpha plus beta will be again at W. It's very simple. So that will imply by the C alpha plus beta property, the W, which is the intersection of all collection of subspaces of V, will in turn be a subspace of V. Now we get a movement which is nothing but there exists a smallest subspace of V which contains S, where S is any collection of vectors of V that is a subspace which contains S and which is contained in every other subspace having S. So for that, we are moving to the definition connected with the word span. Let S be a set of vectors in a vector space V. The subspace spanned by S is defined to be the intersection W of all subspace of V which contain S. So if S is a subset of V, what is the subspace spanned by S? You have to think about all W, let A belongs to some text inside. Okay, where these WAs are subspaces of V. So S is a subset of V. Then you have to say that S is a subset of WA as well as subspace. Subspace. Okay, so if S is a subspace of all these WAs, then S is nothing but the intersection of all those WAs, A coming from some indexing set. Okay, that's what the subspace spanned by S means. Then S is a finite set of vectors. That means let S is equal to set alpha 1, alpha 2, etc. alpha n. We shall call the subspace to be spanned by the vectors alpha 1, alpha 2, etc. alpha n. Okay. The Now we are going to give a more good notions about the subspace spanned by a subset S, which we talked about and defined earlier. The subspace spanned by non-empty subset S of a vector space is nothing but the set of all linear combinations of vectors in S. So what we talked about here, this one is nothing but the set of all linear combinations of elements inside S. Okay, to prove that, let W be a subspace spanned by S. Okay, you're fine. That means this W is equal to intersection of all subspaces of V which contain S. Right? Now, then each linear combination which is given by alpha is equal to x1 alpha 1 plus x2 alpha 2 plus etc xn alpha m, where alpha 1 alpha 2 etc alpha m are in S, is clearly in W. Why is it in W? Yes, because this alpha 1 alpha 2 etc alpha m are in S. Right. So these elements will be in every subspace you are talking about in the intersection. Okay. Just simply take this alpha 1. See, alpha 1, alpha 2, etc. alpha m belongs to S. So these alpha 1, alpha 2, etc. alpha m will belong to uh, we are taking a W to be the subspace spanned by these. So definitely this is contained in W, which is equal to intersection of all subspaces WA which contains S, right? So these elements will be contained in all WA for every A belongs to I. That means if x1, x2, etc., xm are constants inside F, definitely x1 alpha 1 plus x2 alpha 2 plus etc. plus x m alpha m x m alpha m belongs to WA for every A. So if it is inside every A, that means that linear combination will be inside W. Right. It's very trivial. Okay. Thus, W contains the set L of all, that means all the linear combinations of the vectors in inside in S will be inside S. So what we just proved is if L is equal to the linear combinations of all vectors of S, that L will be inside W. That's what we just proved. Okay. Now, the set L on the other hand contains S. It's non-empty, right? Already we said S is non-empty, right? So L is non-empty. Now, if alpha and beta belongs to L, then alpha is equal to x1 we are taking then alpha to be if it is a linear combination, definitely we know that elements inside L will be a linear combinations of elements of S. So alpha 1 alpha 2 etc alpha m. So if alpha and beta are belonging to L, alpha and beta will be a linear combinations of alpha 1 alpha 2 etc alpha m, which is what is written here. Alpha is equal to x1 alpha 1 plus x2 alpha 2 plus etc xm alpha m. Beta is equal to y1 beta 1 plus y2 beta 2 plus etc plus yn beta n, where these x1 x2 etc xm are coming from the field, y1 y2 etc yn are coming from the field, rest of them are vectors inside S. Now For each scalar C alpha plus beta is considered, which is this, that will belong to L, right? Why? Because all these alpha i's and beta j's are inside S. So every linear combination of elements inside S will be inside L. So C alpha plus beta will also belong to L. So what we proved here in the second part, we prove here that if we assume C alpha plus beta belongs to W, C alpha plus beta belongs to W in the sense we are taking that yes, W to be a subspace. W being a subspace, we get every C alpha plus beta to belong to L. That means W subset of L, you get L is equal to W. So to end up the proof, now you have to show that L is a subspace of V which contains S, and also that any subspace which contains S will contain L. It follows that L is a intersection of all subspace containing S. That is, L is a subspace spanned by the set S. So we have show, what did we show here? We show that L is equal to W. We first proved L subset of W, now we prove W subset of L. So that ends our proof. It is also a very easy proof. Next is a definition about sum of vector spaces. If S1, S2, etc., Sk are subsets of a vector space, the set alpha 1 plus alpha 2 plus etc. alpha k, where each of them are coming from alpha 1 coming from S1, alpha 2 coming from S2, etc., alpha k coming from Sk, is called the sum of subsets S capital S1, S2, etc. Sk, and it is denoted by S1 plus S2 plus etc. plus Sk, or by summation I is equal to 1 to k Si. Similarly, if W1, W2, etc., Wk are subspaces of V, the sum W is equal to W1 plus W2 plus etc. plus Wk is this, and we can prove that it is a subspace of V which contains each of the subspaces of Wi. That is, here W is a subspace of V such that W1 belongs to W, W2 to W, and so Wk belongs to subspace of V. So that is an easy proof. You can verify it to show that W is a subspace of V, and W1, W2, etc., Wk are subspaces of W in turn. Now in example 8, we are taking F to be a subfield of the field of complex numbers, and we are choosing three vectors alpha 1, alpha 2, alpha 2, alpha 1, alpha 2, alpha 3, which is the 5 tuple. Alpha 1 is 12030, alpha 2 5 tuple 00140, alpha 3 0001. So a vector alpha in the vector space W of F5. So call it F5. This F5 is nothing but R5. Okay, we are denoting R5 as F5. So keep that in mind. That is the notation we are following here. What we are going to do is, so we are going to develop a subspace W of F5, which is spanned by the three vectors we have taken here. Okay. So if generally alpha is such element inside that span, Remember the word span. Okay, we call it as call it by spanning. Alpha is equal to scalar multiplied by alpha 1 plus scalar multiplied by alpha 2 plus scalar multiplied by alpha 3. So instead of alpha 1, substitute this. Instead of alpha 2, substitute this. Instead of alpha 3, substitute this. And you simplify it like this. Alpha 1 is equal to adding out, you get this 5 tuple C1, 2C1, C2, 3C1 plus 4C2, C3, where C1, C2, C3 are arbitrary scalars we have taken already. Now, W can be described as a set of all 5 tuples. That means the elements inside W were elements like this. We are just rewriting it as if alpha is equal to 5 tuple x1, x2, x3, x4, x5. Uh, this we have seen here, this if c1 is here, this is 2c1. If c2 is here and c1 is here, the fourth one is 3c1 plus 4c2, and this is c3, the third constant. So if x if x1 is here fixed, this will be 2x1, x2 will be 2x1, and x1 and x3 are fixed, then x4 will be 3x4 plus 4x3, right? And x5 here will be the same. Okay, so from that you can check out that the 5 tuple minus 3 minus 6 1 minus 5 2 will be in W, whereas the 5 tuple 2 4 6 7 8 will not be inside W, because it is not of the form which we mentioned here. Okay, example 9 gives us another approach, which says if F is a subfield of the field C of complex numbers and V be the vector space of all 2 by 2 matrices over F. We are going to make subspaces for this V. Uh, Remember, it is 2 by 2. So W1 is equal to, we are fixing it to V. We are taking the fourth, the entry in the second row, second column to be 0. Rest of them X, Y, Z varying inside F. It is definitely a subset of the vector space V we talked about. Okay, and then we are going to think about the subset W2, which is nothing but the entry of the first row, second column, and the second row, first column. Both are zeros. Rest of them X, Y, which are varying inside F. It is also a subset. Okay. Here W1 and W2 are subspaces of V. You can verify it. It is very easy under the same field F. Okay. Also, V is equal to W1 plus W2. Why? Because take an arbitrary element matrix A, B, C, D inside V. Okay. This A, B, C, D inside V can be written as matrix A, B, C0 plus 0, 0, 0, D. Okay. The first matrix is coming from W1 and the second matrix is coming from W2. So any matrix inside V can be splitted like this and added up. That means we can write V is equal to W1 plus W2. It is also a subspace. You can verify it out. Now, yes, definitely V is a subspace. You don't have to verify that. You have to understand that V is equal to W1 plus W2. And also subspace W1 intersection W2, you can just analyze the elements inside W1 is this form, is of this form, and elements inside W2 is of this form. So W1 intersection W2 will be having the form X0, the 2 by 2 matrix X0, 0, 0, because it is the intersection. Okay. Now we move on to the example 10. which talks about a matrix m by n order A over the field F. That means the entries are coming from the F field. Here is nothing but treat it as R. It is the set of all real numbers. Whenever we think about f, that is nothing but r. Fn means Rn. Okay, the row vectors of A are the vectors in Fn given by it is of the n tuple form. Okay, m tuple. Here it is taken m tuple. The subspace Fn spanned by the row vectors of A is called the row space of A. So we had earlier discussed an example when we chose alpha 1, alpha 2, alpha 3. Okay, these take these as rows and form a matrix. So, so what you get as the matrix here is A is equal to 1 2 0 3 0 0 0 0 1 4 0 0 0 0 0 1. The same rows we take here. So this is a row vector 1, row vector 2, row vector 3. And we had formed a linear combination of those row vectors, right? And we said the linear combination will be W. The subspace formed will be W is equal to x1, x2, x3, x4, x5 with the conditions x2 is equal to 2x1, x4 is equal to 3x1 plus 4x3. So this is a subspace over F. Okay. We are saying that if we have a matrix here with rows the same, then what we define as W will be called the row space of the matrix. Now we are thinking about a matrix B with the first three rows coming as the same row vectors and the third row something different. Then also what we talked about is a row space of the matrix. We are taking the row space of the first three vectors. So that's an important word term you have to keep in mind, row space. Now example 11 says that if V be a space of all polynomial functions of f. So you know how the polynomial functions looks like a0 plus a1x plus a2x square plus etc plus anx raised to n. We are taking from those polynomial functions s, which is nothing but x raised to n. We are just taking x raised to n. Then V is a subspace and where n is varying from 0, 1, 2, etc. That means nothing. S is equal to if n is equal to 0, you get x raised to 0 is equal to 1, then x squared, x cube, etc. Right? So when we are taking polynomials, we are taking actually the combinations, linear combinations of these elements where the coefficients are coming from f, that is R. So V is a subspace spanned by this set S. That is a inference you get from example 11. Now you have the exercise section. The first four of the exercises should be solved in the next class, and the next five questions, 5 to 9, should be solved in the next section. So that's all for today. So thank you for watching this video and do work out with the lecture notes. Thank you again.